So in this case, let's look at stability of atoms, the basis for that. So here we are just going to introduce ourselves to a very critical concept that's going to run through all atoms, through the entire chemistry, right? Everybody wants to be stable. You want to attain financial stability yourself, right? You want to be independent. You want to be stable, right? So the same thing happens to the atoms. And we say that the atoms come together, they form compounds, they form molecules, they form whatever in the previous sessions, right? So now we are going back to the atoms and look at how do they achieve that stability, right? What makes them attain that stability? Now we know that some cases electrons are lost, electrons are gained. In which cases should they do that? And if they are doing that to form ions, right? You say that formation of the ions is with the concept of them becoming stable with other compounds or with other atoms. So let's look at the basis. Why are they doing that? Right? So stability of atoms basically. This is the model of the atom that we have been using from the beginning of this video, from the beginning of this series, right? And then we were like, with this model of the atom, we labeled it and we say these are shells and all that. But then there's something externally that we want to add at this point. You can watch a video on the introduction to chemistry, the ones we've done so far, where you can understand how we label this model so far. Here we are going to add a bit of knowledge. We say that the outermost shell, this shell, that is the very last one. So if this is the middle, right? The nucleus is here, and you have this first shell, this is second shell, and this is third shell, right? So for this last shell, the biggest one, the largest one, we call it, this one we call it, let me call it we call it outermost shell. Outermost shell, that's the outermost, right? The one that's very outermost shell. The one that is inside, this one, this very first one after the nucleus, is called the innermost shell. Innermost, meaning it's very inside, right? Innermost shell, right? But all of them are called shells. So this one, the second one here, you just call it all these that are inside, the innermost, and the one that we call it inner shell. Then the one that's allowed is the outermost shell. So the very last one, the largest one, is the outermost shell, and all the other one that are inside we call the inner shells. But then the one that is very close to the nucleus, that become, if all of them that are inside are called the inner shells, the one that is very inside, the very first that is closer to the nucleus, is called the innermost shell, right? It's just English. Okay, so those are the names. So another name for the outermost shell is valence shell. That's another name for the outermost shell, the very largest one. It's a very critical shell for us. It's very important shell for us. That's the shell that hosts all the valence electrons. So all the electrons that are on the valence shells, we call these valence electrons, right? And the valence shell hosts all the valence electrons. So we can call these electrons outermost electrons. You can call them valence electrons. They are the ones that contribute to the valency. That's if you want to remove an electron or add an atom, you have to first encounter the first innermost shell, the outermost shell. So that's the electron that can be removed or added, easily removed or added, right? They are the one on the outermost shell. So we call them valence shells. So right, so all the electrons of the outermost shell or the valence shell are called valence electrons. All the electrons that are inner, we call them inner electrons, or we can call them core electrons. The one that are inside, right, we call them core electrons. They are in the core of the atom. The core is like the inside of the atom, so it's core electrons, right? Core electrons are located on the inner shells, and then outermost electrons or valence electrons are located on the valence shell or the outermost shell, the valence electrons. So in this case, you can see these valence electrons around it. This is valence electron, 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 another one. But all the other ones that are inside the inner shell, all of them are called core electrons, right? These one they have special name called the valence electron, valence shell, valence electrons. Okay, there has been a lot of repetition on the same thing, right? I just wanted you to understand, and then I think the repetition will help you know that I'm stressing on something very important for you to know, right? Okay. Now we know what valence electrons and all that. Then why? Then stability. How that stability comes in, right? Atoms follow some two basic rules. You have the octet rule, and then you also have the doublet rule, duplet rule, doublet rule. Okay, so there are so we say the shells are the one that holds the electrons, right? Based on the number of electrons, we have some number of shells. You need to have the allowable number of shells in order to allocate it. But this is how you have to know that the first shell is a label, has a label. The label for the first shell is the K shell, L, M, in that order. So the very first shell is called the K shell, is the K shell. We have the K shell, the L shell is the second one, the M shell, any other one, M, N, O, P, Q, R, S, T, just normal. So I start from K. The K shell is the very first shell, right? So the very inner shell is called the K shell. This is the K, L, and then M. If there is another shell, we will call it N. If there is another one, M, N, O, right? In that order. Okay. But this is what you have to know. The K shell. The K shell, so K shell is shell 1. So you count from the inside. Shell 1. So number 1, you can shell 1, shell 2, shell 3 going. Okay. So now the number of electrons that a shell can host. The number of electrons that a shell can host has follow this formula. So they say the number of electrons on a shell is going to be 2n squared. 2n squared, where n is the number of the shell. So shell number 1. So this is not like a neon. This is not be like a neon. I mean number of electrons. 2n squared, where n is the number of the shell. Which shell number is that? We always count from the inside. So this one is shell number 1, right? It's going to be, so the K shell is going to host how many electrons? 1 squared, which is going to be 2 times 1, that is going to be 2 electrons. So always 2 electrons are on the first shell. That's 1 and 2. Now let's go to the second shell, shell L, right? Shell L, the n is what? 2 over there. So 2 squared. So we are going to have 2 times 4, which is going to be 8 electrons. So the second one, there's going to be 8 electrons as well. The third one, shell N, yeah, right? K, L, M. Okay, M, sorry. So that will be the third shell. We're going to do it like this. At the end of the day, have 2 times 9, which is going to be 18 electrons. So a maximum of 18 electrons can be on the third shell in that order and distance, right? That's what we've covered so far in things. But then to simplify from JHS, we know that this is not the rule that we follow, right? We know JHS, we have K, shell K, L, M, N, right? So what we do is that we at that level they just tell you that 2 electrons should go here, the next one should take 8, the next one should take 8, the next one should take 8, maximum of 8. This is the very basic one that they taught us when we were in junior high school, right? 2, 8. The other, so the first one takes a maximum of 8. Any other shell that follows has to take a maximum of 8 electrons. Remember, you only knew from hydrogen to calcium, and calcium has 20 electrons, right? 20 electrons inside it. So that's what we knew to when we were in JHS. But now that you are going to, there's going to be this linear formula that we'll be using. But depending on the timing of using that, I will also tell you. But right now, let's try to understand this very basic thing. Okay. Now, this just means that every atom, right? So we are going to use this as a logic. We are going to use this as a logic to understand. We are going to use this 28818 to as a logic to understand this stability and the groupings in the table. This is linked to the groupings in the periodic table. So 288. So every electron, right? So following that, for the very first shell, you need to have what? A maximum of 2 electrons. When it has 2 electrons, then it is stable. That is called the double is like 2 doublet rule. This is a doublet rule following 2. Now the 8 is the octet. Octet is 8, meaning that the valence shell or the outermost shell should have 8 electrons. The shell wants to have 8 electrons in maximum to do that. So based on this particular thing that you knew first already, right? We are going to see how it's linked to the periodic table. So periodic table that we looked so far has been something like this. We had the S block, P block, and all that. So, but then the periodic table that I'm going to show you, the simplest one, is we are going to keep these guys away for now. We are going to keep these guys away for now and focus on the main group element. The main group element. So these are the main group element, right? These guys and these guys, the main group element. So the next table that I'm going to show you are just going to be periodic table without the transition metal. So these are the main group elements. The main group are the one that has A. Why is A? We did that in the previous sessions, right? So group 1A, group 2, 3, 4, 5, 6, 7, up to group 8. So you see that 2, 3, 4, 5, up to 8, right? Because the octet rule, we said it so far. We are going to use that basic knowledge to actually proceed with this one. We are going to assume that we are going to learn more stuff about the filling of electronic configuration, the full one. But right now, we are going to use what you know to make you understand the basic things about the periodic table. Okay, so these elements are in group 1, right? So based on the number of electrons on their shells, right? That's why they are labeled like this. So consider like, okay, all the elements in group 1, if you go to their valence shell, that's the outermost shell, there's going to be only 1 electron there. If you go to the group 2, the same thing, 2 electrons there. Group 3, 3 electrons. Group 4, 4 electrons. 5, 6, 7, up to group 8. For the group 8, meaning that valence electron is having 8, right? If the valence electrons is having 8, what does it mean? It is already stable. We say that they all want to be stable. They all make sure that their valence electrons are 8 in number. For the doublet rule, it's only hydrogen and helium that needs to follow that. Only hydrogen and helium that just want a maximum of 2, right? Hydrogen and helium, because they have only 1 shell. But then what happens for the number of electrons on the shell? The number of electrons on the shells, right, tells you that, okay, then this is in group 1, right? So group 1 to up to this last one. This is what they do. So group 1 elements have 1 electron in their valence shell. Group 2 elements have 2 electrons on their valence shell. Group 3 like that, 4, 5, 6, 7. So this is the basic thing that you need to know. That's how you used to actually get it, based on what you know, before we can proceed with the detail. There's more to that, but right now, what you know is very helpful to understand the periodic table. It's going to help us a lot. Okay, I also want you to know something, that this, if you look at row-wise, row-wise, this first row tells you that the row is telling you the number of shells. So we call it the period. The period, we see the period, right? And these are the groups. So then the period, then the number of the period tells you the number of shells those group of atoms have. So this is period 1. So this hydrogen and helium have only 1 shell. So if they have only 1 shell, that should be the very first shell, right? The K shell. And the K shell has a maximum of 2. That's why they are limited like that. But if you come to the next one, this is period 2. For the period 2, they need to have what? 2 shells. 2 shells. So they have the inner shells, and they have the K shell and the L. The K has 2 electrons, and the L shell wants to have what? 8. I need to have a maximum of 8, right? So this period 3 also have what? 3 shells. Period 4 has elements have 4 shells. In that order, I'm to get down. Now the period tells you that the groups, which is looking like this, is telling you the number of electrons on these shells. So if I take boron, for example, boron is in period 2, right? If boron is in period 2, meaning boron has 2 shells. So K shell and the L shell. And then how many electrons are on the valence electrons? The valence electron is going to be 3 because it's in period 3. So group 3, so 1 electron, 1 electron, 1 electron. This is a simplified version, right? So if you use these basics, you'll be able to identify and put an atom somewhere. When you see it, you know that, okay, this particular atom should have 3 electrons, and then it's in this period, so this is the number of shells that you can have and all that, right? Yeah. This is going to form the basis of building on the stability that we want to know, right? I want to pause here for you guys to rewatch this thing. If you understand this very well, then join me in the next video where we actually build on this. We are still in the basis of atomic stability, right? We are going to do that, and then we are going to understand or build on that in the next video, and then from there we'll be able to name some basic compounds and form some small chemical substances, right? Compounds, and then be able to name them. When we name them, then we go to John Dalton and understand what they are saying about the atoms all this while. See you in the next session.